What if we told you that the James Webb Space Telescope, NASA's highly anticipated successor to the Hubble, can make terrifying discoveries that could change our understanding of the universe forever? Well, it's true. Recent developments have revealed that the JWST is poised to uncover some of the most mysterious and potentially disturbing phenomena in the cosmos, from black holes to dark matter to the possibility of alien life. Strap in, because the discoveries that await us are truly out of this world. What is the James Webb Telescope? The James Webb Space Telescope, JWST, is a large, infrared optimized space telescope that was set to launch in 2021. It is named after James E. Webb, who served as the second administrator of NASA from 1961 to 1968 and played a key role in the Apollo program. The JWST is considered the successor to the Hubble Space Telescope and is expected to greatly expand our understanding of the universe. It is designed to study a wide range of astronomical phenomena, including the formation of galaxies, the birth of stars, and the atmospheres of exoplanets. With its powerful instruments and cutting-edge technology, the JWST is poised to revolutionize our understanding of the cosmos and take us one step closer to answering some of the most fundamental questions about our place in the universe. The terrifying discoveries that the James Webb Telescope is capable of. 1. Seeing farther into the past than EVR-BFOR. To see the precious rare photons from the most distant galaxies in the universe, the bigger the telescope, the better, and space telescopes don't come bigger than JWST with its 21-foot, 6.5 meters, primary mirror. But that's only half the job done, because the more distant an object is, the more its light is redshifted. The farther a galaxy is from us, the faster it is receding from us because of the expansion of the universe. So the more its light becomes stretched, shifting the light toward redder wavelengths. The most distant galaxies, which are also the earliest galaxies we can see, emit light that is shifted into near-infrared wavelengths by the time it reaches Earth. It's this redshift that prompted scientists to design JWST to specialize in near and mid-infrared light. The combination of the large mirror and infrared vision has enabled JWST to see more distant, earlier galaxies than astronomers ever have before, promising to transform our understanding of how these galaxies form. 2. Discovering Voyager Elite UPIV, the UNIVADE RC. Following the Big Bang, but before stars and galaxies had formed, the universe was dark and shrouded in a fog of neutral hydrogen gas. Ultimately, light, particularly ultraviolet radiation, ionized that fog. But where did that light initially come from to end the cosmic dark ages? Astronomers believe that light came either from young galaxies filled with stars or from active supermassive black holes, which are surrounded by accretion disks of brilliantly hot gas and shoot powerful jets into space. The question of which came first, galaxies or their black holes, is one of the biggest conundrums in cosmology, a kind of chicken or egg question. Already, JWST has found that the early galaxies it is detecting are brighter and more structured than expected, with distinct disks around bulbous cores already filled with stars. This characteristic suggests that fully formed galaxies were on the scene quickly, but whether they already contained supermassive black holes remains to be seen. 3. JWST MES URE's EXOPLANET atmosphere. Astronomers have now found more than 5,000 exoplanets and counting, but despite this remarkable haul, we still know next to nothing about many of them. JWST isn't designed to discover new exoplanets, but it does aim to paint much more detailed pictures of known worlds by conducting something called transit spectroscopy. When a planet passes in front of its star, some of the star's light filters through the planet's atmosphere, and molecules in the atmosphere can absorb some of that starlight, creating dark lines in the star's spectrum, a barcode-like breakdown of light by wavelength. Knowing what's in a planet's atmosphere, or even whether it has an atmosphere at all, can teach astronomers about how a planet might have formed and evolved, what its conditions are like, and what chemical processes are taking place in that atmosphere. Early results have been hugely encouraging. In August, astronomers announced that JWST had made the first confirmed detection of carbon dioxide gas in the atmosphere of an exoplanet, in this case, WASP 39 bits, which is 700 light-years away. 4. WEBB CRCES for scientists of life and AABITABLITI. Studies of planets such as WASP 39 bits are one thing, but one of the holy grails of exoplanet science is to find another planet that is habitable, like Earth, and JWST is well positioned to characterize alien worlds. The aforementioned observations of WASP 39 bits bode well for forthcoming studies of the planets of the TRAPPIST-1 system of 7 rocky planets orbiting a red dwarf star located 40.7 light-years away from Earth. 4 of these worlds lie in the star's putative habitable zone, where temperatures would permit liquid water. They could potentially be habitable to varying degrees. Initial observations with JWST are focusing on TRAPPIST-1c, which is the easiest to observe. Models predict that it will have an atmosphere similar to Venus, with lots of carbon dioxide. While TRAPPIST-1c is likely too hot to be habitable, determining whether it has an atmosphere, and if so, whether that atmosphere possesses carbon dioxide, will be a big step toward characterizing Earth-sized worlds. 5. JWST studies cosmic chemistry and galaxy evolution. Some stars live for billions upon billions of years, but others exist for just a short time before either exploding in a supernova or expanding to become a red giant that then puffs off its outer layers into deep space. In both situations, the stars disperse large amounts of cosmic dust formed from elements heavier than hydrogen and helium across space. It turns out that there is a relationship between a galaxy's mass, its star formation rate, and its chemical abundance. Deviations from this relationship at high redshift might indicate that galaxies evolved differently in the early universe. Before JWST, astronomers could only reliably measure the abundances of various elements in galaxies up to a redshift of 3.3. In other words, galaxies that existed about 11.5 billion years ago. But how abundant these heavy elements were in galaxies earlier than this is a bit of a mystery, and fertile ground for JWST to revolutionize our understanding. Early results from JWST have shown that the relationship between star formation and mass does hold for galaxies at redshifts as high as 8, but that their abundance of heavier elements is 3 times lower than expected. 6. JWST CTS its sights on the solar system. Although JWST was designed to probe deep space, it can also be used to observe our nearest neighbors, and the results have been pleasantly surprising. Astronomers were not sure what to expect when JWST pointed at Jupiter because of how fast it moves and how bright the planet is compared to the faint distant galaxies JWST usually observes. Scientists worried that Jupiter might overload JWST's sensitive detectors or wipe out fainter features with its glare, but the results were better than could be imagined. JWST's images showed Jupiter's faint rings and some of its small moons, as well as the planet's atmospheric bands and auroras. By observing in near and mid-infrared light, with the high resolution that JWST's giant mirror provides, astronomers can peer deeper into Jupiter's atmosphere to see what's going on beneath the cloud tops and learn how deeply the clouds extend. 7. JWST is teaching us about star formation. One of the Hubble Space Telescope's most iconic images was that of the Pillars of Creation, columns of molecular gas many light-years long found in the Eagle Nebula. Those columns are cosmic nurseries where stars are born. JWST has revisited the Pillars of Creation, and the resulting images in near and mid-infrared light are just as special as the original. But the new views are also more than just pretty pictures. JWST's infrared vision can penetrate through the dust in the pillars to gain a better view of the star formation going on inside, showing knots of molecular gas on the verge of collapsing into nascent stars. When those stars are just a few 100,000 years old, they begin to shoot out jets that erode the edges of the pillars. Elsewhere, JWST has provided one of the most detailed looks at such a protostar known as L1527 and how it is interacting with the molecular gas that is accreting onto it, prompting outbursts that are clearing out 2 cavities in the butterfly-shaped nebula. 8.